Hello, everyone, and welcome back. This is the MHF4U course, Advanced Functions, Grade 12 University, and we are in Unit 1. This is going to be Lesson 1 of 2 parts. And for today, we're going to be having a look at exponential functions and their inverse. And so in general, we're going to be studying functions and their inverse, and in specific, we'll be having a look at studying exponentials and their functions and their inverse, as well as a look at some properties of these. So we will summarize those at the end of the lesson. In general, we'll know that the class has gone well because you'll be able to sketch an exponential function and its inverse. For technology today, I have the Desmos scientific calculator as well as the Desmos graphing calculator for us today. So why do we are interested in the inverse of an exponential function? Well, in general, it's useful because we're going to be able to solve equations of the form 10 to the power of x is equal to 2500. And there's nothing special about, say, 10 to the power of x. The special part is that previously we might have looked at how to solve equations like 2 to the power of x is equal to 8, and then realize that 8 is the same thing as 2 to the power of 3, which implies then that x is equal to 3. However, for these kinds of equations, we're trying to solve of the form 10 to the power of x equals 2500. And we can't write 2500 with a base of 10. And so we need to figure out a different method for solving these. We can try to that the power of 3 equal to 10 to the power of 4,000. So we need 1,000 is 20, sorry, 1 and 10,000. We conclude that the answer has to be between 3 and 4. Okay, so if you have 10 to the power of something between 3 and 4, you're going to get 2,500. You can use graph technology to figure out what that is exactly. So like 10x, and I type in y is equal to 2,500, you can see that that value is going to be about 3.397474, but we want to be able to figure out use it. So that to solve such way. But we need to review what a function and not a function, we need to review what are special class functions that oh, all right. Sorry. Here to have bad weather here today. It's dropped me from my call here, but that's okay. We are back. And so inverse functions are a special class of functions that undo each other. So here the input and output for two inverse functions or for two functions are shown. F of x is equal to 2x plus 1 and g of x is equal to x minus 1 over 2. And they're shown here on the graph. So you can see here the original function is in red. This f of x is equal to 2x plus 1. And the inverse function is shown here in blue. This is the g of x is equal to x minus 1 over 2. So some patterns you'll notice about this is if you have a look at the input for the x and f of x values, so you can see we get 0 and 1, 1 becomes 3, 2 becomes 5, 3 becomes 7. If we have a look at the inverse function, we can see we have 1 and 0, 3 and 1, 5 and 2, 7 and 3 with respect to ordered pairs. If you notice, the inverse of the function appears to be the original function's coordinates swapped around. So the point 0, comma 1 becomes the point 1, comma 0. The point 1, comma 3 becomes the point 2, 3, comma 1, and so forth. And indeed, that's what we mean by undo each other. Okay, so inverse functions have a lot of special properties. This is one of them. Another property that these will satisfy that we don't study in this course, and we denote an inverse function or the inverse of a function as f negative 1 of x. So this is what we call the inverse. Okay, a special property of these is that if you evaluate f of negative 1 of f of x, that'll be the same thing as f of the inverse function of x, which is just going to be equal to x. So this is what we call the composition form, but this is a topic we're going to be studying much later in the course. But just note for now that if it fulfills this property, you may have already seen this before, but I thought it worthwhile. Another consequence of an inverse function is that these will reflect each other across the line of reflection, y is equal to x. Okay? So if you were to flip this red function across the line y is equal to x, you end up with the blue function, the inverse function. Okay? And so just in summary, notice that the input of the first function, f of x, becomes the input for the second function, g of x. So the output of the first function becomes the input of the second. The output of the second is the input of the first. So in order to graph a function in its inverse, a very common method, and this is what we're going to be doing for this lesson, is to first graph the original function and then the inverse by switching the x and y coordinates. If you so choose, you could also algebraically determine an inverse. And so we can do this by taking our x and y and swapping them. So here, if we start with the original equation, y is equal to 2x plus 1, we can solve for the inverse by swapping the position of x and y. So we make this x is equal to 2y plus 1, and then we solve for y. Okay, so we minus 1 from both sides, so this becomes x minus 1 is equal to 2y, divide by 2, and we'd have y is equal to x minus 1 over 2. And you notice here, that's exactly the equation of the inverse. And so we would denote this with that f negative 1 term. Okay? And so specifically now, we're going to be having a look at exponential functions and their inverse. And so we're going to mimic what the book says here, and because it's reasonably explained. The graph of the exponential function, y is equal to a to the power of x, is reflected in the line y is equal to x. And note that x and y are just elements of real numbers, which means they can be whatever you would like. As a result, y is equal to a to the power of x becomes x is equal to a to the power of y. This latter function is what we denote as the inverse. Okay, so if you notice here, and I'll highlight this, the red function, this y is equal to a to the power of x, will be reflected and become this blue function. X is equal to a to the power of y. And this is what we're interested in, the study of this blue function and its various properties. Okay, so notice that the domain of y is equal to a to the power of x, meaning what x values we're allowed to have, become the range of x is equal to a to the power of y. So the x values we can have in the first function become the y values we can have in the second function, and the y values we have in the second function become the x values we can have in the first function. Traditionally, when referring to the inverse function, we use the notation f negative 1 of x, although with the inverse of an exponential, we'll call that something special later. So note that the original function, has a horizontal asymptote at y is equal to 0. So here we have a horizontal asymptote that the exponential approaches but never gets to. That will then be reflected across the line y is equal to x. And in the inverse function, that'll become a vertical asymptote with x equals 0 as its equation. Okay? And so for example 1, we're going to sketch an exponential function and its inverse. And so this is broken up into several steps, but over a couple of pages, but we'll go through this now. So we're going to graph f of x is equal to 5 to the power of x. And so to do this, we choose typical x values around the origin. Okay? Usually for exponential functions, we want to choose x is equal to -1, 0, and 1 is usually okay. But for us, we're going to include the 2 and -2 just so that way we get a very clear picture. Okay? So we're going to substitute these values into the function and go ahead and evaluate them. Okay. So choosing our x values, -2, -1, 0, 1, 2, we have corresponding y values. So f of -2 will be equal to 5 to the power of -2. Okay. So on our calculator here, if we type in 5 to the power of -2, you can see here we get 0.04. If we type in f of -1, that's 5 to the power of -1, which will give us 0.2. Next one is 0. So if we type in f of 0, that's 5 to the power of 0, which you may recall is 1. But if not, we can just go ahead and type that one in. The next value we have is 1. So if we type in f of 1, that's equal to 5 to the power of 1, which is just 5. And if we type in f of 2, that'll equal 5 to the power of 2, which is going to be 25. Okay. And again, if you're ever unsure about these, you can go ahead and type these into your Desmos calculator to help confirm that these are the case. And so what are going to be our corresponding x and y values? Well, oh, sorry, there we go. And so here, if x is equal to -2, y is equal to 0.04. So this ordered pair becomes -2, comma 0.04. The next one becomes -1, comma 0.2. 0 goes to 1. 1 goes to 5. And 2 goes to 25. And so those are each of the ordered pairs points we're going to use. So we're going to plot these on the graph and sketch them with a smooth curve. I pre-plotted what this looks like because it's a lot easier for me on a tablet to do this because trying to use the stylus here is a little bit difficult for connecting the points. But you get the familiar J curve. So note that we got our points here, 1, 5. There's 2, 25, 0, 1, and so forth. Okay, so that's part 1. We graphed f of x equals 5 to the power of x. Next thing we're going to do is we're going to sketch x is equal to 5 to the power of y, which is the inverse of that function we just sketched. So the way we're going to do this is we're going to make use of the fact that the domain of y is equal to f5 to the power of x is the range of x is equal to 5 to the power of y. And the range of y is equal to 5 to the power of x is the domain of x is equal to 5 to the power of y. So what all that means is we effectively take the ordered pairs we found in the table above and, quote, switch them. Meaning that if we have a function f of x is equal to x comma y, the inverse will be just y comma x with respect to their ordered pairs. And so we can take and plot them on the curve and sketch them. And so I took the points from above. So note these values of -2, -1, 0, 1, and 2 evaluated as a given function. And all I did was switch their position. Okay, so -2 comma 0.04 became 0.04 comma -2. -1 comma 0.2 became 0.2 comma -1, and so forth. And so we end up with this sketch of the graph. Okay, and so this is what they look like. And these would be reflections of themselves across the line y is equal to x. I'm not going to sketch that in just because my y-axis goes up by quite a bit, actually. And if you notice, I can't even switch the point 2 comma 25 because it jumps off my sheet. In fact, I would have to scroll way far out to the right to get to it. Okay, so that's what sketching these things looks like. So let's do another one for practice purposes. We're going to do a more difficult one. We're going to try to sketch y is equal to 1/2 to the power of x and its inverse, as well as the line of reflection. And I did graph the line of reflection for this one. Okay, so let's go ahead and try this out. And so we want to evaluate this function at the given x values given. So we're going to take 1/2 to the power of -2, 1/2 to the power of -1, 1/2 to the power of 0. And if you want to as well, you can just make the stipulation that 1/2 is just equal to 0.5. And this will save on the amount of space we need to use. So 0.5 to the power of 1 and 0.5 to the power of 2. So typing these in, if I were to type in 1 divided by 2 to the power of -2, we get 4. And note if I were to type in 0.5 to the power of -2, I still get 4. It's the same thing. 1/2 to the power of -1 is going to give us 2. 0.5 to the power of 0 is going to give us 1. 0.5 to the power of 1 is just 0.5. And 0.5 to the power of 2 will be 0.25. Okay, so the ordered pair we're going to work with will be -2 comma 4, -1 comma 2, 0 comma 1, 1 comma 0.5, and 2 comma 0.25. Okay, so when we graph this on our table here, so our first point is -2 comma 4. That's going to be up here. The next point is -1 comma 2, then 0 comma 1, and 0.5 comma 0.5. Sorry, 1 comma 0.2, 0.5. So I gotta go one more over. So that's here. And then 2 comma 0.25 is here. So this is what the inverse will look like. Okay, and you've studied this shape of graph before, but if not, that's okay. That's why we're covering it here. Okay, so this is the equation y is equal to 1/2 to the power of x. And if you want the inverse now, x is equal to 1/2 to the power of y, all we need to do is switch the ordered pair. So instead of x comma y, we now have the point x. -2 comma 4 becomes comma -2. Negative comma 2 becomes the point 2 of 1. 0 becomes 1. 1 point becomes 0.5 comma 1. And 2 comma 0.25 becomes the point 0.25 comma 2. And so we can graph these on our graph now. So 4 comma negative 2 would be here. Next one is 2 comma negative 1, which is here. Next one is 1 comma 0, which will be here. Next one is 0.5 comma 1, which will be here. And the last point will be 0.25 comma 2, which will be here. And again, we can just make those dots nice and big. And when you're graphing this yourself, it doesn't need to be perfect. Just as long as it is as close, reasonably close, that's okay. Okay, so we will connect it onwards. And we will label this. This is now x is equal to 1/2 to the power of y. And so you can see for this, this is a little bit different from the graph from above. So you can see it was much cleaner. Does the same here. We have a in the x is equal to at 0, and then original function y is equal to x. We have a horizontal asymptote of y is equal to 0. And I mentioned that so I can't use a short form until I type it out once. This is horizontal asymptote. And here is our vertical asymptote. Okay, so for an asymptote, and these asymptotes define end behavior. And so it's a value that the function gets really close to, but never gets to. An example of like these ones in work is if you imagine you have a chocolate bar on a table, somebody takes half of it, then somebody takes half of the half. So there's a quarter. Somebody takes half of that half, then half of that half, and so forth. Technically, you never run out, even though in reality, the piece would be so minuscule it might disappear. Okay, so these are what the graphs of these particular functions would look like. Okay, and so now we're going to denote a new function, a logarithm. And you might be thinking, oh, have we seen this logarithm before? Not necessarily, but if you notice here, we have a log button on our calculator. So if you have a scientific calculator that you're using, you should have this log button. That's the short form for logarithm. So if you see a logarithm, that's the same thing as log, which looks like this. Okay. So all functions have an inverse, but the inverse of an exponential function has a special name. We call the inverse of an exponential function introduced to denote this function. So the exponential form of the inverse is x is equal to a to the power of y. That's really clunky notation, just because typically we like defining equations in terms of y depending on x, not x depending on y. But we can write the logarithm as y is equal to log base a of x. Okay? And so if you see y is equal to log base a of x, this is equivalent to x is equal to a to the power of y. Okay? And so the way we read these things is if you have y is equal to log base a of x, it is read as y is the logarithm of x to base of x. Okay. Sometimes we will also write this as y is equal to log base a. Sometimes we put brackets around the part that's being affected by the logarithm, like such. That's just, and because sometimes it gets a little complicated in there, so we call that part we do like to put brackets around there sometimes. Okay, so we have various properties. So here, this is y is equal to 2 to the power of x, and y is equal to log base 2 to the power of x. Sorry, log base 2 of x. And so we can do this on Desmos as well. Oh, just going to squeeze this out for a second. Let's refresh this. Yep. We'll reload. Okay. And so just to show you that this is the inverse, if we type in y is equal to 2 to the power of x, here is this specific function. So there's 2 comma 4 as an example. And then you can see 3 comma 8 is also on here as well. Okay. And if we were to type in x is equal to 2 to the power of y, we get the inverse function. Well, I wonder if I can click this. No, I can't change the color on the Desmos one as easily. I got these from my computer. But I can show you that this blue curve is equivalent to this y is equal to log base 2 of x. So if I type in y is equal to function, should be somewhere on here. You can see that there's a log base a button. So I'm going to click that. And so if I type in 2 and x into here, you can see that this is the exact same function. Okay, so how I got there again, to be clear, I typed in y is equal to, then I clicked on functions, and I had to scroll quite far down. So I had to get to the calculus portion, and I'm looking for this log base a button. So this is log base a 2 of x, like so. And so we can end up getting that curve. Okay, and so let's have a look at some properties now. So we're going to have a look at the domain and range, as well as any x-intercepts, y-intercept, vertical asymptote, and horizontal asymptote. Okay, so for y is equal to 2 to the power of x, the domain is what? Well, remember, the domain is the range of x values that we're allowed to have in a function. So the domain of y is equal to 2 to the power of x would be x is an element of all real numbers. So x can be whatever you would like. Because remember, if I try to type in 2 to the power of anything, I can get an answer, no problem. And so that's why it's going to be the range has to be x is an element of all real numbers. However, for the range of this, y is equal to 2 to the power of x, if you notice, we can only have values above the y-axis. Sorry, above the x-axis. So we would say that y is an element of all real numbers, but y must be greater than 0. Okay? And that's because there is no solution, like say 2 to the power of x. So there is no number such that when you take 2 and raise it to a power, you get -1. That has no solution. Okay. What about the domain? Well, the interesting thing is I already, based on the domain and range of the exponential, I can already get the domain and range of the inverse. So here, the domain of y is equal to log base 2 of x will be the range of y is equal to 2 to the power of x. So here, we will have x is an element of all real numbers, but x must be greater than 0. Okay, so if you notice on our graph here, our function does not exist to the left of the y-axis. Okay, So we can't get over here with our green function. It doesn't make any sense. And that's because it's the opposite of the 2 to the power of x equals -1, or the inverse, I should say. Conversely, though, the range will be the domain of x, but in y. So here we're going to have y is an element of all real numbers. Okay, and so if you notice here, this graph will go down infinitely far down below, and we get very close to the vertical asymptote, but we never actually approach it. So we have values, they just get, as you get closer and closer and closer and closer, they kind of shoot down towards negative infinity. Conversely, if you as you take log base 2 of larger and larger numbers, this part increases slowly, but it will increase towards positive infinity. Okay? So if you imagine here in and I have the right log, just know it doesn't have log whatever, but in log of your number takes quite a while to increase. Whereas if I type in logarithm of a very small number, so 0, 0, 1, starts going off towards the negative numbers. Okay. What about an x-intercept? Well, for y is equal to 2 to the power of x, there is no x-intercept. So we just not applicable. For the y-intercept, and now take the inverse of this. For the green function, we now have an x-intercept at 1. And there is no y-intercept. So should that going to be not applicable? About the vertical for y is equal to 2 to the power of x, there is no vertical asymptote, but there is a horizontal asymptote of y is equal to 0. By a similar token, if we have a look at the vertical asymptote of y is equal to log base 2 of x, that's going to be, instead of y equals 0, that'll become x is equal to 0. And similarly, there is no horizontal asymptote, so this will be not applicable as well. Okay, so you can see this symmetry where we have the inverse characteristics are true. So the opposite domain and range, so forth, the opposite x and y intercepts, the opposite vertical and horizontal asymptotes. Okay. The only trait that these do have in common is that, and we'll study this topic later, but both functions, and I'll write this in blue, are increasing across its domain. So previously you might have studied increasing and decreasing. And what we mean by that is if you read a graph from left to right, does your finger go up or does your finger go down? If your finger, if you as you're tracing along the curve, trends upwards, that means a function is increasing. And if you notice, both the graph of y is equal to 2 to the power of x and y is equal to log base 2 of x, they are both increasing across its domain. That is a characteristic that a function and its inverse will share. Okay. And so all the properties that I listed above here for this are true for the case where the base of the logarithm or the exponential is either greater than 0 or between 0 and 1. Okay. So if we notice for this graph here, the generic case of what this function would look like is y is equal to a to the power of x with the condition that a is greater than 1. So if I were to graph this on Desmos, y is equal to say 3 to the power of x, all of these kind of graphs would look very similar to each other. And similarly, the logarithmic equivalent will look the same. However, when you have a value of a between 0 and 1, you'll end up with this shape instead. So if I try to type in y is equal to, say, 0.4 to the power of x, we end up with this shape. And again, and this is a value of a, where a is between 0 and 1. So if we were to type in, say 0.9 or 0.3, 0.2, 0.1, they all have a similar corresponding shape, as well as the inverse. Okay, and so that's what I did put here in this note. So in the above graph, we said that in this case, a is equal to 0.4. And so where that leads us to will be for tomorrow, but I thought we'd give a little bit of just a little bit of a teaser for tomorrow. We can now solve questions like 10 to the power of x equals 100. And so if you have 10 to the power of x is equal to 2500, its inverse would be x is equal to log base 10 of 2500. And if you check it out, if on the calculator here, if I now were to type in log of 2500, I get that answer 3.39794 that I had from earlier. So if I type in 10 to the power of 3.9794, we can see we get a value that's approximately 2500. And again, the more decimal places that you include here, the more accurate your response will be. Okay, but that's going to do it. That's going to be us for today. Tomorrow, we're going to be actually studying this more in detail as we convert between exponential and logarithmic form. So if you have any questions, please feel free to reach out, and I'll see all of you next time. Goodbye.